Hey everyone, and welcome back. Have you ever stopped to think about how a platform like eBay can handle millions of bids flying around every single second without ever dropping a single one? Well, today, we're going to look under the hood. We're going to deconstruct the system design of a massive online auction platform, building it piece by piece from just a simple idea to an absolute powerhouse that can scale to millions of users.
All right, so first things first, let's make sure we're all on the same page. An online auction is, at its heart, pretty simple. A seller lists an item, buyers place bids, and whoever has the highest bid when the clock runs out wins. Simple, right?
Well, that's the thing. The idea is simple, but the engineering behind it is anything but. How do you actually make sure that when two people bid at the exact same millisecond, the system gets it right? How do you guarantee that a user's winning bid isn't just lost if a server crashes? That is the monster of a challenge we're tackling today. So here's our game plan. We'll start with a basic blueprint. Then we'll build a simple first version. From there, we'll dive into the most critical part, the bidding engine. Then we'll face a crisis, build a truly fault-tolerant solution, and finally, scale our system to handle an absolutely massive load. Let's dive in. First up, the blueprint. Before we write a single line of code, we have to define the rules of the game. We need to know what our system absolutely must do, and just as important, how well it needs to do it. Let's start with what we call the functional requirements. This is basically what the user can actually do. At its core, a user needs to be able to post an item for auction, they need to be able to bid on an item, and they need to be able to look at an auction and see what the current highest bid is. These are the table stakes. But this is where the real engineering begins. These are the non-functional requirements. We need strong consistency. That means every single user sees the exact same highest bid at the exact same time. No exceptions, no delays. The system has to be fault-tolerant. Losing a bid is completely unacceptable. Bids have to show up in real time. And finally, the whole thing needs to scale to support 10 million auctions happening at once. These 4 rules will drive every single architectural choice we make from here on out. Okay, so you gotta start somewhere, right? We're gonna build a really simple first draft that just handles those basic functions. This will give us a foundation, something we can build on as we start to tackle those much tougher requirements. So the flow for just creating an auction is pretty standard stuff. A user on their phone or computer, that's the client, sends a request. An API gateway, which is like the front door to our whole system, routes that request to a dedicated auction service. That service checks the data to make sure it's valid and then saves it into a database. Simple, clean, a great starting point. Now for the fun part. Creating auctions, that's pretty low traffic. But bidding is a completely different beast. This is the high-stakes, high-traffic heart of our platform, and it absolutely needs its own specialized engine. So you might be asking, why make a totally separate bidding service? Well, this is a really critical architectural decision, and it comes down to 3 big reasons. First, scale. We expect something like 100 times more bids than new auctions, so these 2 things need to scale independently. Second, complexity. The logic around bidding is super tricky, and we want to keep it isolated. And finally, performance. The bidding service has to be optimized for an insane number of rights, while the auction service is really all about reads. And with our simple design, we've just walked headfirst into a crisis. It's a classic textbook problem in distributed systems called a race condition. And in our case, it could actually cause 2 different users to think they've won the same auction. A total disaster. Just look at this timeline. The current high bid is $10. User A and user B both load the page and see that $10 value. Now, user A submits a great bid of $100, but before that new price can get back to user B's screen, they submit your own bid of $20. The system checks their $20 bid against the stale $10 value it read earlier and accepts it. Catastrophe. And the consequence here is just brutal. This isn't some tiny technical glitch. It's a catastrophic failure of trust. If users can't trust the platform to record their bids correctly, the entire system is basically worthless. So how do we fix this nightmare? We need to build a system that's not just consistent, but completely fault-tolerant. We can never lose a bid, not even if our servers literally catch on fire. This quote from the source material just says it all. The durability of bids is absolutely non-negotiable. It's a core promise of the entire platform. So how do we actually guarantee it? The solution is to introduce a durable message queue. Now, the best way to think of this is like a restaurant's waiting list on a busy night.
When a bid comes in, we don't try to process it right away. We immediately write it down on this super reliable list. Now, even if our bidding service gets totally overwhelmed or even crashes, the bid is safe. The queue acts as a buffer, holding all the incoming bids until the service is ready to process them, one by one in the correct order.
A technology like Apache Kafka is basically purpose-built for this job. It can handle insane throughput, millions of messages a second. It's durable because it writes every single message to disk, and crucially, we can partition it. Think of this like having separate dedicated waiting lists for each individual auction. This lets us process bids for thousands of different items, all in parallel, making sure that a bid for a vintage car never gets stuck in line behind a bid for a comic book.
Okay, our system is now reliable and it's consistent. The final challenge is scale. How do we get this design to handle 10 million concurrent auctions?
And let's just put that scale into perspective for a second. At peak, we are talking about 10,000 bids hitting our system every single second. That is an immense amount of write traffic that we have to handle flawlessly.
So how in the world do we do it? We break it down. For our services, we use what's called horizontal auto-scaling, which is a fancy way of saying we just add more servers as the load increases. For the database, which would melt under 10,000 writes per second, we sharded it. Sharding just means we split our one giant database into lots of smaller, faster ones. We can use the auction ID to make sure a bid always goes to the right little database, spreading the load perfectly. And for those real-time updates, we use a publish-subscribe system, or pub/sub. It's like a radio station. When a new high bid is confirmed, it publishes that update, and every user watching that auction is subscribed to instantly get the news. And there you have it, our final architecture. We've got our separate auction and bidding services, we've got our Kafka message queue for durability, a sharded database to handle all the writes, and a pub/sub system for real-time updates. Every single component we added directly solves one of those critical non-functional requirements we talked about at the very beginning.
So what are the big takeaways here? First, always start simple and then iterate. Second, you have to identify and isolate your high-traffic components, just like we did with our bidding service. Third, use message queues like Kafka anytime you need rock-solid durability and a buffer against sudden spikes in load. And finally, when you hit the right limits on your database, sharding is your best friend. We've designed a robust, scalable system. It can handle the load, it won't lose your data, and it keeps everyone updated in real time. It feels complete. But in the world of system design, there's always another challenge right around the corner.
So I'll leave you with this final question from the source material. Forget about fixed end times. How would you design a system to handle dynamic endings, sometimes called popcorn bidding? It introduces a whole new fascinating set of challenges around timing and state management. Think about that one, and thanks for watching.